Ludovic Berthier finished his PhD as the École Normale Supérieure de Lyon in 2001. After that, he became a Marie Curie postdoctoral fellow at the University of Oxford until 2004. He has been a visiting scientist at the University of Chicago. He became a CNRS Director of Research at the University of Montpellier in 2009. He has recently been awarded the Silver Medal of the CNRS for his 25 years of research. So welcome, Ludovic. Thank you for the very nice talk this morning and for giving us the time for this interview. So I wanted to start with maybe something of a personal question. So did you ever see yourself doing something different from physics?
The short answer is yes, a lot of things. I think I decided to do physics very late, just when I started to do a PhD. So between age 0 and the time of my PhD, I tried to think about different things, and convergent physics very, very late, I think. So of course, as a kid, I wanted to do all the things that kids want to do, dentist, fireman, and everything. And then I think during my studies, I converged slowly towards science first and then physics. But then I think, yeah, it wasn't a planned thing.
And what do you feel are the most rewarding aspects of being a scientist and the biggest challenges?
Being a scientist, I don't know. I think when I decided to become a scientist, I had zero idea what it meant. And it's just after these many years that I realized what it means. I'm not sure I would have done it if I knew the challenges, which is it's a lot of work. Rewards that are often not gigantic. That is, you pursue an idea, you try to solve a problem for many months, and then at the end you're happy with yourself, you have a paper. So you have to find your rewards mostly by yourself, and sometimes it's easy, sometimes it's not. So finding, the energy and the will to pursue research, that is a challenge, I think. Not everyone can do it, and this is hard, I think. That's probably the most challenging part.
Can you share with us now the key aspects, the key moments that you took during your career that took you here?
I decided that, engineering schools or working on big companies was not for me. So this is where I decided to a school called École Normale in France, École Normale Supérieure, where you are trained to be either a teacher or a scientist. And this is, I think, the moment I decided this was what I liked best. Probably in my studies was, at the end of this, you have to choose either you go and teach or work in a company if you want, or you go into research and do a PhD. And that's probably the moment where I decided that, yes, research is appealing to me. The people I saw doing research and, you do internships and you try it and you go into labs. And that, I think it's the moment where I decided I liked it. And then, of course, if you keep working and you want to go and enter academia and research, then the choice of a PhD, the choice of a postdoc, the choice of a lab and everything, this is important, but it's already extremely focused. If you want to succeed, you have to be supervised by the right people, you have to be at the right places, and that is a bit of it's collisions, but you also make decisions. It's half is randomness and chance and luck, and the other half is what you can do to direct your motion, if you wish.
So now we are going to start getting into the theme of your research, which is glass systems. So as you know, glass has been worked for a long time, since the Middle Ages, and people have become really expert at working with it.
Yes.
So what really inspired you to get into this field and study glass systems?
Yeah, so it's a good question. I have it all the time. I mean, the field of glass physics, it's really gigantic. There are many subgroups of people who all work on glasses but don't know each other. So many people are asking or using glasses or trying to understand something about glasses, but they really work in different worlds. So in a sense, I'm only working in a small subfield of glass research. the questions that we are trying to answer and explain, and you know, the theories that we construct, the simulations we do to understand certain behaviors. This is not 3,000 years old. It's really modern research, and I try to give this perspective in the talk that, you know, the theory of the glass transition, the statistical physics, the deep understanding of what's going on at the glass transition has been a slowly constructed field. It started maybe 100 years ago, and then there were key papers. So yes, it's an old field, but the progress has been slow, yet it's steady. You know, new things are being done, new simulations are being done, new questions are being answered, new theories are being constructed as we speak now, despite the fact that the materials were invented by the Egyptians or whatever. So that's how I say that it's this slow construction, and the minute you answer one question, there is another one to be answered anyway, because there are so many things we don't understand yet about glasses.
So how would you define a glass? How is it different from, say, a crystal?
So there are two questions in your question. The second one is easy. So the crystal and the glass are two pieces of solid material that, you know, when you look from outside may look like each other. Yet if you look deep down and you have a tool to measure how the atoms or the molecules are organized at the, you know, at the microscopic scale, you can immediately tell the crystal from the glass. The crystal has this periodic order of the atoms that the glass has not. The structure of the glass looks like the one of the liquid from which it was created. What is the glass is more complicated. I think the example I gave in talks to get started is you all know glasses. You drink with glasses, you have window glasses, you know what it is. But the minute you start to think about an actual definition, that's where you get lost, because, you know, most glasses that we use are being created by taking a liquid at high temperature, slowly cooling, and when it's cool enough, it's a glass. When it's hot, it's a liquid, and in between there is no specific temperature where something big happens, and you say, oh, this is the liquid, this is the glass. It's a gradual change. So as all smooth changes, you can't define it because there is no sharp definition that's telling you this is a liquid, this is a glass. But when things are well separated or separated enough, you can say this is a glass. But it's a practical definition rather than a scientific one, if you wish. So most glasses we use are not sharply defined, and yet we call them glasses, you know, in the common sense of the glass transition.
How can you argue that the glass can be a state of matter?
This is where I think you need to do a lot of work. So the answer to the previous question was nothing dramatic happens in the glass as you see it. It's a smooth crossover from the liquid. So whether you call it glass or liquid, it's your choice. Now the question the underlying question that you're asking is, if I could do things differently, if I could do, ideal experiments, would I be able to reveal that something like a sharp definition of a glass can be given? And this is what I think I'm discussing here. And I think we have strong evidence from these many years of statistical physics research and computer simulations now that, yes, if you could do things, with an infinite amount of time, with the largest possible systems, something like a sharp transition between the liquid and the glass, in some cases, could be defined, but it's extraordinarily difficult to observe. So what we are trying to do is find the conditions where this can be sharply defined. And then at least we would say the glass as we know it in experiment is like a reflection of this phase transition that we have discovered that in these specific conditions can happen. In practice, it's really difficult to observe, but what we observe is the direct consequence of this underlying phase transition. So this is how at least I justify my research.
So I have a question coming from someone who works with crystalline systems.
Okay.
So as you know, for crystals, you use the periodicity of the lattice to study when you have correlated states like superconductivity and magnetism. So how is it possible that glass systems can develop superconductivity and magnetic order states?
And so the broad answer to your question is when we want to compute some properties of solid states of matter, many properties rely heavily on the fact that you have or you don't have periodicity of the lattice. And so transport of heat or electric conduction or mechanical properties depend strongly on this. Some other properties, I think you're asking about superconductivity, are a bit more subtle. They may be a bit less sensitive to the underlying structure. I think for superconductivity, it's not so much the periodicity that maybe in the glass and in the crystal, the atoms are a bit, the density is different, for instance, and it may be that it's more that how close are the atoms that matters compared to is it periodic or not. So for some properties, it's key to know whether you have periodicity or not, and for some others, it's not.
So I was wondering, what theoretical descriptions do you use to study glass systems, and what role does thermodynamics and statistical mechanics play there?
Sometimes we say that so many theories of the glass transitions. It's like a cliche that people give in talks or conferences. I think I would disagree. I think there are many levels of description. Some are, very macroscopic and totally empirical. I think what we are trying to do with the statistical mechanics approach is we are trying to start from the, macroscopic degrees of freedom. I give myself interactions between the particles, and I say, I take n particles like this, do they form a glass, and if yes, in what conditions? This is what statistical physics does. It doesn't start from, a coarse-grained perspective where the degrees of freedom are already macroscopic quantities. So I think what we are trying to do is really, for the glass transition, the most elementary, more microscopic description. You start from the atoms or the molecules, and you want to understand the emerging macroscopic phenomenon. Do you get a solid, or do you get a crystal, or do you get a liquid in these specific thermodynamic conditions? So when we do computer simulations, it's a bit the same thing. We start from microscopic degrees of freedom. We put all the atoms in the computer. We solve their equations of motion, and we see the emerging property, which is either glassy behavior, slow dynamics, crystallization, etc. So computer simulations, the way I was describing, and statistical physics do the same thing. It's about predicting the emerging macroscopic behavior of materials, starting from the microscopic interaction, the microscopic degrees of freedom. And this is why it's complicated, because it's like, you give yourself almost nothing and you have to predict everything. So that's why it's complicated.
Do you think that all this research can help further the field of glass and can impact how glasses are made and the application that they have in our life?
So it's a complicated question, and I have many possible answers to that one. Sometimes the most provocative, it's I don't care. I just want to understand things, and my job is not about finding applications. It's about, trying to construct some deep understanding of things. And so measuring impact in science, it's not straightforward. It's not about only, having a product in a company being manufactured. It's also about helping the work of others, or that's one application for me. It means the research you did has been useful to understand many, many systems. Another application, which is not technological, is you devise, a new algorithm to study your system, and then it can be used by others to ask other questions that you never ask yourself. So if you help the research of someone else, this is how, again, knowledge propagates. So to me, this is a way to have an impact on research. It's not only the end product.
Mm-hmm. So related to the thing you just mentioned, do you think that the scientific community benefits from the collaboration between the theoretical community and the experimentalists?
Of course, I think even if you do theoretical research, I think at least in my field, interacting with experimentalists has been extremely useful. Working with them is also interesting. It's you have a group of people with their way of thinking, and you think very differently. And sometimes doing the to be able to work together, there is a lot of discussions to be had. You have to understand each other. It means you have to explain yourself better. But it's I think it's a positive challenge. But just I think in the scientific communities in general, I think interactions between different people have always been very beneficial.
Thank you. So I have one very last question. What advice would you give to one undergraduate student that would like to pursue a scientific career in research?
I remember when I wanted to become a scientist as an undergraduate, I'm not sure I was ready to follow advice from the old people. So that's why now I'm not sure I want to give advice. It seems to me that all scientists are so different. There are certain things that I like to do, but my colleague in my office, she does science very differently from me. And so that's certainly why people go into science, because they can do and work the way they like. So that's certainly a good thing. And it probably means that scientists are also independent thinkers and don't necessarily listen to the advice of the senior people. The young people, they will follow their path, and they probably don't need to listen to senior people so much.
So thank you very much. That's about it.
Thank you.